We're going to look at applications of exponential functions, and I'm going to show how exponential functions show up all over the place. Okay, and the two big applications that we'll look at today are growth and decay. All right, now starting out with growth, what we mean by growth usually is population growth. And we can characterize population growth like this. P of t, so my population function, equals p sub 0 a to the t power. Okay, now this p sub 0 here, sometimes you say p naught or p sub 0. What this is my initial population. In other words, how much stuff I started out with. And then we multiply that by an exponential expression, a to the t power. And for growth, for population growth, we want a to be bigger than 1. So this models population growth. And if you remember, when we looked at graphs of exponential functions, if a was greater than 1, you had to graph something like this. And so this particular function is going to cross the y-axis at p naught. So in other words, when t is 0, that's how much we start out with. And then as t goes on, it's going to just grow exponentially. So that's what population growth looks like. And we can easily look at examples of this, and I'm going to show you one now. So for our first example, we're looking at population growth. We're talking about a type of fish called the Milo grouper. The Milo grouper population is being introduced into a man-made lake. Wildlife experts estimate that the population will grow according to this model, p sub t equals 1,000 2 to the t over 3 power, where t represents the number of years after introduction. The question asks us for the doubling time. What is the doubling time for this population? Now before we address that, let's point out something here. If you compare that to what we just talked about, this 1,000 is my p sub naught. What does that mean? That means that we introduced 1,000 fish into this lake, right? That's the initial population. Okay, now when it says doubling time, a doubling time means the time it takes to double the population. So in this particular example, what that would mean then is that I want 2,000 fish, right? I started out with 1,000. If you double 1,000, you get 2,000. So I'm going to let the function value be 2,000, and I need to figure out for what value of t does this work. Now at this point, we don't know how to solve a lot of these, but I think we'll be able to solve this one. So what I can do here is divide both sides by 1,000. So if I divide 2,000 by 1,000, I get 2. So I end up with 2 equals 2 to the t over 3 power. Now this is an exponential equation we can solve because we have a common base, right? And I could write this again as saying 2 to the first power equals 2 to the t over 3 power, which means that since I've equated the bases, all I have to need to worry about is the exponents. That means that 1 equals t over 3, or in other words, t is 3. And remember, this is measured in years, so t equals 3 years. In 3 years, the Milo grouper population is going to go from 1,000 to 2,000. And I hope you can see how exponential growth really goes fast, right? All right, let's look at another one. So for part B, we ask, how long will it take for the population to reach 8,000 fish according to this model? It's the exact same thing, okay? We're going to set this time 8,000 to equal 1,000 times 2 to the t over 3 power and solve for t. Hopefully we can do this. So if I divide both sides by 1,000 here, I can see I get 8 equals 2 to the t over 3 power. Okay, this is an exponential equation, but we can work this one out because I can equate the bases because I know 8 is the same thing as 2 to some power. I know that 8 is the same thing as 2 cubed. 2 times 2 times 2 is 8. So 2 cubed equals 2 to the t over 3 power. Now that the bases are equated, I can drop that and just consider the exponents. So 3 equals t over 3, which means multiplying both sides of the equation by 3, I get 9. It's going to take 9 years to go from 1,000 fish to 8,000 fish, according to the wildlife experts model. The second application with exponential functions is with decay, and usually when we say decay, we are talking about radioactive decay. So this is typically with chemical compounds. And radioactive decay is modeled like this. A of t equals a naught times a to the t power. Now that looks just like population growth, doesn't it? And it is. This a naught is our initial amount, in other words, how much substance we started with. And as time progresses, this is going to decrease from radioactive decay. And so because of that, we want our a to be between 0 and 1. If you remember our graphs for these things, it looks kind of like this when a is less than 1. And we'll cross the x-axis at a naught. That's our initial amount. And with radioactive decay, what happens is we have something called half-life. Every substance has a half-life, and the half-life of a substance is the amount of time it takes for that amount of substance to decay to half of its original amount. So now we're going to look at an example of this, and I hope it makes sense. Okay, so now we're going to look at an example of radioactive decay. Here we have carbon-11, which is a chemical compound. It's used as a diagnostic tool in some medical tests. Has a half-life of approximately 20 minutes, which means if you started off with a kilogram of carbon-11, after 20 minutes you now have half a kilogram, okay, because it decays that quickly. So the first thing they asked us to do is determine the value of A, so that A of t equals A sub naught A to the t power, describes the amount of carbon-11 left after t minutes. So in other words, let's find the exponential function for this situation. Okay, now we don't have an initial substance, but we don't really need it, because what we do know, what they did give us this time, is a time, a value of time. 20 minutes is the half-life. So I know that when t equals 20 minutes, and we are measuring in minutes here, I know that when t equals 20 minutes, I'll have half of what I started with, right? So I can say 1/2 A sub naught, that's 1/2 my initial amount, equals A sub naught A to the 20th power. So now I divide both sides by A sub naught, and I have 1/2 equals A to the 20th. So how do you solve this equation? Well, imagine if I had A cubed equals something. I know I would just take the cube root of both sides. Okay, so this time I'm going to actually take the 20th root of both sides here. All right, so I'm taking the 20th root of 1/2. Another way you could write that is 1/2 to the 1/20th power. And so that's my value of A. A is 1/2 to the 1/20th power. And we'd probably want to get that in some sort of number we recognize. So this is approximately, according to a calculator, 0.965936328 Okay, so that's approximately what we get. And that's not a pretty number, but it's one we can work with. All right, let's look at another one. So part B says, look, let's start with a 2 kilogram sample of carbon-11. How much would be left after 30 minutes? Okay, so we just figured out that my A sub t function was my initial amount, and this time we're talking about 2 times 1/2 to the 1/20th power, all that raised to the t power. So here I could simplify this a little bit by saying 2 times 1/2 to the t over 20 power. Okay, now this 30 minutes is a time, and we are measuring t in minutes here, so A sub 30 would be 2 times 1/2 to the 30 over 20th power, or another way of saying that is 2 times 1/2 to the 3/2 power, and then from there we just need to plug it into a calculator. So according to my calculator, I have 2 times this value, and I'm writing out just so you can test to see if you get the same numbers, but that's 0.35355,33906. And I just need to multiply that value by 2. After 30 minutes, we have about 0.7071067812 kilograms. Now, if we started with 2 kilograms, this is less than half of what we started with, which makes sense because our time has gone past 20 minutes, right? 20 minutes was the half-life, so we're past the halfway mark. Now we're just down to 0.7 kilograms when we started with 2. Okay, now these numbers are not pretty, but the numbers are really not that hard. I mean, that's just a calculator. These values are just things for calculators. What I really want to make sure you understand is this initial part. Can you calculate that? Can you figure that out? And then can you plug in the value 30 in for your time? And that's really the application of exponential equations. Now, a good question would be, how do they come up with this stuff? How do they come up with the population models? How do they come up with the half-life models? And for that, you would need a class called differential equations. So if you have any engineering major buddies or anything like that, you should bring it up to them. Say, hey, look, I understand about half-life and population growth, and I know you're talking about, the half-life of carbon-11 and medical experiments and things like that. And they'll get a kick out of it. You can see, I hope, that exponential functions have applications in a bunch of different areas. And we just picked out a couple of them, but they really show up everywhere. If you have any questions on this, I'd be glad to help. And thank you for watching.